Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine waking up one morning to find a second sun blazing in the sky, outshining every star in the heavens. This isn't science fiction, it's the terrifying reality of what would happen if a nearby star exploded in a supernova. Deep in the cosmos, stellar time bombs tick away, waiting for their moment of catastrophic glory. But what if one of these cosmic explosions occurred close enough to Earth to fundamentally alter our planet's fate? A supernova represents one of the most violent events in the universe, occurring when a massive star, typically 8 to 25 times more massive than our Sun, reaches the end of its nuclear fuel supply. Throughout its lifetime, the star maintains a delicate balance between the outward pressure from nuclear fusion in its core and the inward pull of gravity. When the fuel runs out, gravity wins decisively. The core collapses in less than a second, creating temperatures exceeding 100 billion degrees Celsius and pressures so intense that protons and electrons are crushed together to form neutrons. This collapse triggers a rebound effect that sends shockwaves racing through the star's outer layers at speeds approaching 30,000 kilometers per second. The explosion releases more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. For weeks or months, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Currently, astronomers have identified several potential supernova candidates within threatening distance of Earth. The most concerning is Betelgeuse, a red supergiant star located approximately 640 light-years away in the constellation Orion. This stellar behemoth has already entered its final evolutionary phase, showing signs of instability, including dramatic brightness variations and a measurable shrinking of its outer atmosphere. Another candidate is Rigel, a blue supergiant also located in Orion, sitting roughly 860 light-years from Earth. While farther than Betelgeuse, Rigel's extreme mass, estimated at 21 times that of our Sun, makes it equally dangerous. Its intense luminosity and rapid stellar evolution suggest it could explode within the next few million years, which is practically tomorrow in astronomical terms. The definition of near in astronomical contexts requires careful consideration. Supernovae within 50 light-years of Earth would likely cause mass extinctions, while those within 100 light-years could still trigger significant environmental disruption. At distances of several hundred light-years, the effects become more subtle but remain measurable and potentially dangerous to our planet's delicate atmospheric chemistry. Recent observations using the European Space Agency's Gaia mission have provided unprecedented precision in measuring stellar distances and properties. These measurements have refined our understanding of potential supernova candidates and their evolutionary timescales. The data reveals that while no immediate threats exist within the 50 light-year danger zone, several dozen massive stars, within 500 light-years, show signs of approaching their explosive endpoints. The probability of a nearby supernova occurring within human civilization's timeframe remains relatively low. Statistical models suggest that a supernova within 100 light-years of Earth occurs roughly once every 300 million years. However, the consequences would be so severe that even this small probability demands serious scientific investigation. Understanding these stellar explosions and their potential impacts on Earth has become a critical component of astrobiology research and planetary defense studies. When a massive star detonates, it doesn't simply disappear. It transforms into a cosmic engine of destruction that hurls energy and matter across the galaxy at unimaginable speeds. The explosion creates multiple forms of radiation that travel through space at different velocities, each carrying its own unique threat to any planets unfortunate enough to lie in their path. The initial flash of light represents just the beginning of the supernova's assault on nearby space. Within seconds of the core collapse, the explosion generates an intense burst of gamma rays and X-rays, forms of electromagnetic radiation so energetic they can penetrate deep into planetary atmospheres. These high-energy photons race through space at the speed of light, 300,000 kilometers per second, meaning they would reach Earth in the same time frame as the visual light from the explosion. Following closely behind comes the optical light. That would create the terrifying second sun effect visible from Earth. This light carries enormous energy. A nearby supernova could appear as bright as a full moon, remaining visible even during daylight hours for weeks or months. The sustained brightness would disrupt Earth's natural day-night cycle, potentially affecting everything from plant photosynthesis to animal migration patterns. But the most insidious threat travels much more slowly. The supernova's shockwave accelerates particles to near light speeds, creating an expanding shell of high-energy cosmic rays. These charged particles, primarily protons and atomic nuclei, hurtle through space at velocities approaching 90% the speed of light. While they would arrive at Earth only days or weeks after the initial light, their effects would persist for thousands of years as they interact with our planet's magnetic field and atmosphere. The energy distribution of a typical supernova reveals the scale of destruction involved. The explosion releases approximately 10 to the power of 44 joules of energy, equivalent to the Sun's total energy output over its entire lifetime, compressed into a few seconds. About 1% of this energy emerges as electromagnetic radiation, while the remaining 99% powers the expanding shockwave and accelerated particles. As this energy expands outward, it follows the inverse square law. The intensity decreases with the square of the distance from the source. A supernova at 50 light-years would deliver roughly 10,000 times more energy to Earth than we receive from the Sun. Even at Betelgeuse's distance of 640 light-years, the energy flux would still exceed solar intensity by a factor of approximately 25. The cosmic ray component presents particular challenges for analysis. These high-energy particles don't travel in straight lines due to interactions with galactic magnetic fields. Instead, they follow complex, curved trajectories that can increase their travel time to Earth by hundreds or thousands of years. This delayed arrival means that the cosmic ray bombardment from a supernova could continue long after the visible light has faded, creating a prolonged period of enhanced radiation exposure. Modern space-based observatories have revolutionized our understanding of supernova mechanics. The Chandra X-ray Observatory and the Nuclear Spectroscopic Telescope Array, or NuSTAR, have captured detailed images of supernova remnants, revealing the complex structure of expanding shockwaves and the acceleration mechanisms that create cosmic rays. These observations show that supernovae can maintain their particle acceleration for thousands of years after the initial explosion. The Fermi Gamma Ray Space Telescope has detected high-energy gamma rays from several nearby supernova remnants, confirming theoretical predictions about their long-term radiation output. These measurements provide crucial data for modeling how a nearby supernova would affect Earth's atmosphere and biosphere over extended periods. Ground-based neutrino detectors have also contributed vital information about supernova explosions. When supernova 1987 A exploded in the Large Magellanic Cloud, neutrino detectors on Earth recorded the burst of subatomic particles that preceded the visible light by several hours. This detection confirmed that neutrinos, nearly massless particles that barely interact with matter, carry away the majority of a supernova's energy and provide early warning of stellar explosions. Earth's atmosphere serves as humanity's first and most crucial line of defense against cosmic threats, but a nearby supernova would test this protective shield to its absolute limits. The complex chemistry of our atmospheric layers would undergo dramatic changes as high-energy radiation from the stellar explosion penetrates deep into the normally stable regions of our planet's gaseous envelope. The ozone layer, located in the stratosphere between 15 and 35 kilometers above Earth's surface, would bear the brunt of the supernova's assault. This thin layer of triatomic oxygen molecules absorbs 99% of the Sun's harmful ultraviolet radiation, making complex life possible on Earth's surface. However, the intense gamma rays and X-rays from a nearby supernova would trigger a cascade of chemical reactions that could destroy up to 75% of the ozone layer within months of the explosion. The destruction mechanism involves the creation of nitrogen oxides through the interaction of high-energy photons with atmospheric nitrogen and oxygen molecules. When gamma rays strike nitrogen molecules in the stratosphere, they break the strong triple bonds holding the atoms together, creating highly reactive nitrogen atoms. These atoms quickly combine with oxygen to form nitrogen dioxide and nitric oxide, compounds that act as catalysts in ozone destruction reactions. Each nitrogen oxide molecule can destroy thousands of ozone molecules before being removed from the atmosphere through other chemical processes. The efficiency of this destruction means that even a relatively modest increase in nitrogen oxide concentrations can have catastrophic effects on ozone levels. Computer models suggest that a supernova at 50 light-years distance would increase stratospheric nitrogen oxide concentrations by a factor of 100, maintaining elevated levels for several years. The timeline of ozone depletion would follow a predictable pattern. Initial destruction would occur within weeks of the supernova's gamma-ray burst reaching Earth. The depletion would continue for months as cosmic rays from the explosion's shockwave gradually arrive, each wave of particles triggering additional nitrogen oxide formation. The ozone layer would reach minimum levels approximately 2 to 3 years after the supernova, then begin a slow recovery process lasting decades. Temperature changes in the stratosphere would amplify the ozone destruction process. The absorption of high-energy radiation would heat the upper atmosphere by several degrees Celsius, altering the chemical reaction rates that control ozone formation and destruction. Higher temperatures favor the reactions that break down ozone, while simultaneously reducing the efficiency of natural ozone production mechanisms. The mesosphere, located between 50 and 80 kilometers above Earth's surface, would experience even more dramatic changes. This region contains very little ozone, but plays a crucial role in atmospheric chemistry through its interactions with cosmic rays and solar radiation. A supernova's high-energy particles would ionize large quantities of mesospheric gases, creating a layer of charged particles that could persist for years after the initial explosion. These ionization effects would have cascading impacts on Earth's radio communications and satellite operations. The enhanced ionization would create unpredictable variations in radio wave propagation, potentially disrupting global positioning systems, satellite communications, and radio astronomy observations. The effects would be similar to those observed during major solar storms, but lasting much longer and affecting a broader range of frequencies. Research conducted by NASA's Goddard Space Flight Center has used sophisticated atmospheric chemistry models to simulate supernova effects on Earth's atmosphere. These simulations incorporate hundreds of chemical reactions and account for the complex three-dimensional structure of atmospheric circulation. The results consistently show that ozone depletion would be most severe at polar latitudes, where the combination of atmospheric dynamics and magnetic field geometry concentrates the effects of cosmic ray bombardment. The recovery of Earth's atmosphere would depend critically on the continued absence of major cosmic ray sources. Natural ozone production would gradually restore the protective layer, but the process would take 50 to 100 years to return to pre-supernova levels. During this extended recovery period, Earth's surface would remain vulnerable to enhanced ultraviolet radiation, with potentially severe consequences for life on our planet. The collapse of Earth's ozone shield would unleash a cascade of biological disasters that could fundamentally reshape life on our planet. With up to 75% of the protective ozone layer destroyed, ultraviolet radiation reaching Earth's surface would increase by factors of 10 to 100, creating conditions not seen since the earliest days of life's emergence from the oceans billions of years ago. Marine ecosystems would face immediate devastation as ultraviolet B radiation penetrates the upper layers of the oceans. Phytoplankton, the microscopic organisms that form the foundation of marine food webs and produce approximately 50% of Earth's oxygen, are extremely sensitive to UV radiation. Laboratory studies have shown that even modest increases in UV exposure can reduce phytoplankton reproduction rates by up to 40%, while the intense radiation from a supernova aftermath could eliminate entire species of these crucial organisms. The death of phytoplankton would trigger a collapse of marine food chains within months. Zooplankton, small fish, and marine mammals that depend on phytoplankton for food would face starvation. The effects would propagate upward through the food web, ultimately impacting large marine predators, seabirds, and human fishing industries. Computer models suggest that marine productivity could decline by 70 to 90% in the years following a nearby supernova. Terrestrial ecosystems would suffer parallel destruction as enhanced UV radiation penetrates forest canopies. And grasslands. Plants lack the mobility to escape dangerous radiation levels, making them particularly vulnerable to UV-induced DNA damage. Crop plants would be especially susceptible, with agricultural yields potentially declining by 50 to 80% in the most affected regions. The combination of reduced crop production and marine ecosystem collapse would create a global food crisis unprecedented in human history. The effects on human populations would be swift and severe. Enhanced UV radiation would dramatically increase rates of skin cancer, cataracts, and immune system suppression. Populations living at high latitudes where ozone depletion would be most severe would face the greatest risks. The World Health Organization estimates that a 50% reduction in ozone levels would increase skin cancer rates by 600% and cause widespread blindness due to UV-induced cataracts. DNA damage would extend far beyond surface tissues as cosmic rays from the supernova penetrate Earth's atmosphere and magnetic field. These high-energy particles can cause genetic mutations in all living organisms, potentially leading to increased cancer rates, birth defects, and reduced fertility across species. The genetic damage would be cumulative, building up over the years of enhanced cosmic ray exposure following the supernova. Forest ecosystems would face a dual assault from UV radiation and cosmic ray bombardment. Tree canopies would provide some protection for understory plants and animals, but the trees themselves would suffer severe damage. Coniferous forests at high latitudes would be particularly vulnerable, as many evergreen species are extremely sensitive to UV radiation. The death of these forests would release enormous quantities of stored carbon dioxide into the atmosphere, potentially accelerating climate change. Polar regions would become virtually uninhabitable for most life forms. The Earth's magnetic field channels cosmic rays toward the poles, concentrating the radiation dose in Arctic and Antarctic regions. Combined with severe ozone depletion at high latitudes, these areas would receive radiation doses lethal to most complex organisms. Polar ice caps would become sterile wastelands, eliminating critical habitat for polar bears, penguins, and countless other species. The recovery of Earth's biosphere would be a process measured in geological timescales. Even after the atmosphere begins to heal, the genetic damage inflicted on surviving species would persist for millions of years. Evolutionary biologists estimate that it would take 10 to 50 million years for biodiversity to recover to pre-supernova levels, assuming that civilization and technology could survive the initial catastrophe. Some organisms would prove remarkably resilient to the supernova's effects. Deep-sea creatures living near hydrothermal vents would largely escape the radiation, as would organisms living in caves or deep underground. Certain bacteria and archaea possess sophisticated DNA repair mechanisms that could help them survive the genetic damage caused by cosmic rays. These survivors would form the foundation for life's eventual recovery on a dramatically altered Earth. Historical precedents suggest that life on Earth has survived similar catastrophes in the past. The Ordovician-Silurian extinction event 450 million years ago eliminated 85% of marine species and may have been caused by a nearby gamma-ray burst or supernova. However, the complexity of modern ecosystems and the dependence of human civilization on stable, environmental conditions make our current situation far more precarious than anything life has faced before. Despite the catastrophic scenarios painted by supernova research, humanity is not entirely helpless in the face of these cosmic threats. Advanced astronomical surveys, theoretical protective technologies, and the sheer statistical improbability of a nearby supernova provide reasons for cautious optimism about our species' long-term survival in a universe filled with stellar explosions. Modern astronomical monitoring has reached unprecedented levels of precision and coverage. The European Space Agency's Gaia mission has measured the positions, distances, and motions of over 1 billion stars with extraordinary accuracy, creating the most detailed map of our galactic neighborhood ever assembled. This data allows astronomers to identify potential supernova candidates and track their evolutionary status with remarkable precision. Ground-based surveys like the Catalina Sky Survey and the Lincoln Near-Earth Asteroid Research Project, originally designed to detect dangerous asteroids, also monitor stellar brightness variations that could indicate approaching supernova explosions. These automated systems scan the entire visible sky multiple times each month, accumulating data that helps scientists understand stellar evolution and predict future explosive events. The James Webb Space Telescope, or JWST, represents the cutting edge of supernova research capabilities. Its infrared instruments can peer through cosmic dust clouds to observe the internal structure of massive stars, revealing details about their nuclear burning processes and evolutionary timelines. Early observations have already refined estimates of when nearby supernova candidates like Betelgeuse might explode, generally pushing these events further into the future than previously thought. Theoretical protective measures against supernova radiation have been proposed by various research groups, though none are currently feasible with existing technology. Concepts include space-based solar shades that could partially block incoming radiation, atmospheric engineering techniques to accelerate ozone recovery, and even proposals for underground cities that could shelter human populations during the worst periods of radiation exposure. The most promising near-term protective strategy involves genetic modification of crop plants to enhance their UV resistance. Agricultural researchers have already developed UV-tolerant varieties of rice, wheat, and soybeans that could maintain productivity even under enhanced radiation conditions. These crops incorporate genes from naturally UV-resistant organisms like certain bacteria and extremophile organisms. Atmospheric engineering presents longer-term possibilities for mitigating supernova effects. Theoretical proposals include the controlled release of ozone-producing chemicals into the stratosphere, the deployment of high-altitude balloons carrying ozone generators, and even the use of space-based platforms to supplement natural ozone production. While these technologies remain largely theoretical, rapid advances in atmospheric chemistry and aerospace engineering make them increasingly plausible. The statistical reality provides the greatest source of comfort regarding supernova threats. Current estimates suggest that a supernova capable of causing mass extinction on Earth occurs within 50 light-years roughly once every 300 million years. A supernova at Betelgeuse's distance, while concerning, would not necessarily trigger a complete extinction event, though it would certainly cause significant environmental disruption and challenges for human civilization. Recent re-evaluations of Betelgeuse's distance and evolutionary status have been encouraging. Observations from the Hubble Space Telescope and ground-based interferometry suggest that Betelgeuse may be farther from Earth than previously thought, possibly as distant as 700 light-years. At this distance, even a supernova explosion would be spectacular, but not necessarily catastrophic for Earth's biosphere. The diversity of life on Earth provides additional reasons for optimism. Previous mass extinction events have demonstrated life's remarkable ability to recover and diversify after catastrophic setbacks. The Cretaceous-Paleogene extinction that eliminated non-avian dinosaurs 66 million years ago was followed by rapid evolutionary radiation that produced the modern mammalian fauna, including eventually our own species. Human technological capability continues to advance at an exponential pace. The same technologies that allow us to detect and study potential supernova threats also provide tools for mitigating their effects. Advances in genetic engineering, atmospheric science, space technology, and renewable energy systems all contribute to our species' resilience in the face of cosmic catastrophes. The exploration and eventual colonization of other worlds represents humanity's ultimate insurance policy against cosmic disasters. Multiple independent human settlements scattered across the solar system would ensure that even a catastrophic supernova could not eliminate our species entirely. While interstellar colonization remains a distant prospect, the establishment of self-sustaining settlements on Mars, the Moon, and other worlds within our solar system appears increasingly achievable within the next century. Perhaps most importantly, the study of supernova threats has enhanced our appreciation for the fragility and preciousness of life on Earth. Understanding our planet's vulnerability to cosmic forces reinforces the critical importance of protecting our environment, advancing our scientific knowledge, and working together as a species to ensure our long-term survival among the stars.